Well, it's a pleasure to be back here in Cambridge at the Newton Institute. So I'll talk about a simple holographic model of nonlinear conductivity. And to begin, let me just remind you of the standard method of computing conductivity in a holographic setting or through a gravity dual. So the first step is to find an appropriate static black hole solution to represent the equilibrium configuration of the system. Then, since we want to compute conductivity using linear response, all you have to do is to perturb this solution. And you perturb the solution with boundary conditions corresponding to putting a homogeneous electric field, say of strength E, on your system. So that means that in terms of a perturbation of the vector potential, you require that it asymptotically approach this for some harmonically oscillating electric field. The time derivative of this just corresponds to an electric field on the boundary. And finally, the induced current is read off as a sort of 1 over r correction to this perturbation, and you can write that in a gauge invariant way as simply the asymptotic value of r squared times the xr component of the perturbed Maxwell field divided by the xt component. This is the induced current, and that's the applied electric field. Now, most of the time, the solution, the black hole solution, has to be found numerically. The perturbations have to be computed numerically. And so this is a numerical calculation. So the plan for the talk is to present a simple holographic model in which you can do everything analytically. The solution is analytic. The calculation to compute the conductivity is analytic. And moreover, we're not going to calculate the conductivity using linear response, but to do it exactly in a way in which you actually see the Joule heating of the system. The system heats up, and the black hole in the bulk is getting bigger. It's so simple that I can explain it to you in less than the 40 minutes I have. And so in the remaining time, I'm going to give you an update on a program I've been working on for a year and a half now, about calculating conductivities in models where we include lattice effects through a periodically oscillating chemical potential. Okay, so let's begin. This is work I'm doing with Nabil Iqbal, who's here, and George Santos, an excellent postdoc in Santa Barbara, who's actually going to join your faculty in a year. The paper should be out very soon. Okay, so the model is the following. We're simply going to consider four-dimensional Einstein-Maxwell theory with, of course, the negative cosmological constant. And we start with the planar Schwarzschild ADS black hole. So that takes a form that you're all familiar with, where F is r squared minus this constant r naught cubed over r. R naught just sets the scale. It sets the temperature of the black hole. This is dual, as you know, to a 2 plus 1 dimensional conformal field theory with the temperature, which is 3 over 4 pi times the constant r naught. And this CFT is at 0 chemical potential. There's no induced charge density. Okay, so now we want to compute the conductivity. Well, it was computed, of course, using this linear response back in 2007. By Sabir Sachdev, Chris Herzog, and a few other collaborators. And they found that the conductivity was, the optical conductivity as a function of frequency was in fact independent of frequency and just constant, just equal to 1, the appropriate normalization. This calculation, well, this was like the first calculation ever of applying gauge gravity duality to a condensed matter system. So let's start by redoing that in a different way. We'll start with the DC conductivity. At linear order, it's easy to see that a Maxwell field which is constant, just the xt component equal to a constant E, solves the linearized Maxwell equation on the Schwarzschild ADS background. That has the right boundary condition of applying an electric field at infinity, but unfortunately it's singular at the horizon. It may not look singular, but of course the time coordinate is badly behaved there. If you square f, you see that it goes like 1 over f. F is vanishing at the horizon, so this Maxwell field is in fact badly behaved at the horizon. So to obtain a well-defined Maxwell field, well-behaved, you want to use good coordinates at the horizon. So we'll use ingoing Eddington coordinates. We define r star in the usual way. dr star is dr over f. Define v to be t plus r star. So v equals constant surfaces or just ingoing radial light rays. The metric, Schwarzschild ADS metric in ingoing Eddington coordinates, takes the form here. It's minus f dv squared plus 2 dv dr plus r squared times the flat metric. Now in these coordinates, a solution of the linearized Maxwell equation that has the same boundary condition at infinity is simply that f xv equals a constant e. This solves the Maxwell equation. It is now regular everywhere because these coordinates are regular everywhere. And so that's the solution we want. If you rewrite this in terms of the original Schwarzschild coordinates, you see there's an fxt equal to e. And then there's also, this dv includes the dr over f term. So it also includes an fxr component, which goes like e over r squared. That corresponds to a current which is equal to E from the formula I gave, and therefore the DC conductivity is 1. Well, this is computed using linear response, but now it's easy to write down the nonlinear solution. This Maxwell field is null. There's no sort of VV component in the inverse metric. dV is null. And so the only non-zero component of the stress tensor is a VV component, which goes like E squared over R squared. And that corresponds to an ingoing flux of null energy. But we know the exact solution with a stress tensor of this form. That's called the Weige metric. And so the exact solution of Einstein-Maxwell with this Maxwell field is just a Weige metric, which has the same form as Schwarzschild over here. The only difference is that the coefficient of dV squared now becomes V dependent and looks like R squared minus 2 m of V over R, where this function m of V is what we had before, an R naught cubed over 2, plus E squared times V. This corresponds to a black hole, which is growing in time. And in fact, it's growing in time at exactly the rate you would expect from Joule heating in the dual conductor, because the derivative of mass, dm dv, is just E dot j. J is equal to E, because sigma was 1, and so that's just E squared, and that's the solution we have. The Maxwell field in the full nonlinear solution is still constant. This fxv equal to E is an exact solution in the Weige metric, and so J is still equal to E, or the DC conductivity is still 1, even beyond linear response. So that's the DC conductivity, but one can easily generalize this to time-dependent electric fields. If you set the Maxwell field, the xv component, to be any function of V, then, and you let this function, the mass function m of V, to be this constant r naught cubed over 2, plus now an integral of E squared dV, you again get an exact solution of the Einstein-Maxwell equations. The metric still has the same Weige form, and F is just given by that. So you now can turn on an electric field at any rate you want, keep it constant for a while, and turn it off. You have an exact solution for that. Or you can have the electric field oscillate at any frequency you want, and you have an exact solution for that. And for an oscillating electric field, you find from this solution right here that J, as a function now of time, must be equal to E. And so the sigma, the conductivity, stays 1 as a function of frequency, even nonlinearly. It's really that simple. OK, a few comments about this solution. There is a current, clearly, but no momentum. The metric doesn't have any cross terms between t and x, or t and y. So there's no momentum in this geometry. But this is exactly what you'd expect. We start with a system with no net charge density. So the current consists of say, electrons going in one direction and an equal number of positrons going in the other direction, opposite direction. They both contribute to the current, but they cancel out in the momentum. So that's what we expect. You might have thought that with an electric field being produced or being applied to a conformal field theory with massless particles, you would have a pair creation. And so, in fact, when we started, we thought that the current might increase in time, even for a constant electric field, due to pair creation of charged particles. That's not what the solution says. The solution says that you apply a constant electric field, you get a constant current. So that puzzled us a little bit until we found this paper by Green and Sonhee, 2005, which explained that for a constant electric field, you can have a constant current because Schwinger pair creation of particles is balanced by a quasi-particle scattering, which sort of takes charges out of the current. And so you get stationary solutions that way. And finally, I should mention that the same idea of using a time-dependent electric field for this XV component of F was used earlier, back in 2010, by Karch and Sonhee to describe nonlinear solutions of the dBi action. So this is the Dirac-Born infield action, which is a form of nonlinear electrodynamics. They don't include back reaction back on the metric, so they don't see the Joule heating of the black hole, but they do talk about this as an interesting solution of the dBi theory.
They did find some field dependence of conductivity, right?
Here.
Yes.
Oh, yeah. Well, sorry, not in this case. When they were studying this solution, they found that the conductivity was again 1. Yeah. Okay, so far everything's been very familiar. It's reproducing what we expect, but this was a little bit of a surprise. We noticed that we apply, of course, an electric field in one direction. You generate current in that direction, but the metric remains perfectly isotropic in the x and y direction. It's just, the usual r squared times dx squared plus dy squared. And that means that if you compute the stress tensor, the boundary stress tensor, which is the stress tensor of the dual theory, it remains totally isotropic. So why should you get an isotropic pressure if you're having current flowing in only one direction? Well, a hint comes from the fact that this seems to be true only in 4 dimensions. And in fact, it's easy to see it's a consequence of S-duality, or electromagnetic duality, in the bulk. Because under this transformation of F going to the dual of F, with our ansatz for F, the electric field and the induced current rotate from the x direction to the y direction. And the metric stays totally unchanged. So S-duality implies that the pressures have to be equal. But that's an answer from the gravity side. What's the explanation from the dual CFT side? And, well, we don't know. But here's a guess. In the dual CFT, it suggests that when you apply an electric field and generate a current in one direction, you somehow induce a flow of vortices in the perpendicular direction. This is suggested by the isotropy of the pressure and the fact that under S-duality, your particles are interchanged with vortices. So this raises a question of whether this is, since it comes out of the simple gravity calculation, might this be true for all 2 + 1 CFTs with an S-duality symmetry? Or maybe all CFTs, all relativistic ones, or maybe we have to add some more qualifiers. But anyway, this is something raised by this work, which we don't really...
What's saying it's self-duality? You're talking about CFT that's self-duality.
Self-duality. Sorry, I don't mean that it's dual to some other theory. Exactly. But if you have a CFT which is self-dual in this sense, might it be that you always have this property that the pressure remains isotropic?
Harry, do you mean that when you generate the current, then you will at the same time have a flow of vortices, Or you mean there exists a lot of frame which you have a flow of vortices but does not have a current?
No, we mean at the
So
same
what is
time.
in the same frame?
Yeah, it's the same frame. The same frame, because in our theory, without applying any S-duality, we have equal pressure. So it should be in the same frame.
So you can't check this just by applying the CFT S-duality to the stress tensor?
Do we get what?
I'm surprised that you can't answer your question by repeating the S-duality calculation on the CFT side. I mean, Witten has this correspondence between bulk S-duality and S-duality in the CFT, so there's some handle you can crank on the CFT stress tensor to see what the S-duality transformation does to it.
Okay, that would be interesting. Yes, we haven't looked at that. So you say there's, okay, Witten has a discussion where he says what S-duality does to the stress tensor of the dual CFT. That's what you're saying?
Oh.
I mean, it must be the same as what happens in the bulk, right?
The most calculation already done.
Okay, so it's the calculation we've done.
Change the boundary conditions.
So I don't think it's going to tell us anything new. It won't be a microscopic explanation about what the vortices are doing, presumably.
There's some controllable CFT which has self-dual where you can actually compute with it.
That's the right question. Actually, we do have, I was going to ask you about this after the talk. There's some papers which discuss this, right, as you must know, in these quantum Hall systems with the Hall plateau transition. Anyway, let me move on. Okay, but now there's actually a sense in which this isotropy holds even for systems which are not self-dual under this S-duality, because it's easy to see that if you replace the Maxwell action with any polynomial of f squared, the theory will no longer be invariant under electromagnetic duality, but the solution remains the same. Our Weijers and our Maxwell field remain a solution for any Lagrangian, which is Einstein gravity coupled to any polynomial function of f squared, simply because f squared is 0 for this solution. And so we only pick up the first term. And this raises a question now, is there a more general principle? So it's not just S-duality, which is implying isotropy. It's something more general, which implies isotropy. And this was a point also raised by Karch and Sonhi when they were discussing generalizations of the dBi action for nonlinear electrodynamics. Okay, so now let me change gears a little bit and say, what happens if we apply an electric field to an insulator, but treat the problem nonlinearly? There's, again, a very simple solution for a 4-dimensional bulk, dual to a 2 + 1-dimensional insulator. And you can get that by starting with a magnetically charged planar black hole in ADS, and simply analytically continuing, say, y to be a new time coordinate, the time to be a new space coordinate, and analytically continuing the magnetic field into an electric field. So when you do that, you get a metric like this, just f d theta squared, dr squared over f, r squared times now dx squared minus d tau squared. The function f takes this form. You have a mass parameter m naught, and now this electric field comes in with a minus sign because we've analytically continued from the magnetic field. When E is 0, this is a very familiar solution. It's known as the ADS soliton. Rob Myers and I discussed this about 15 years ago as a simple model for a confining ground state of a gauge theory, but in the sort of modern language, it's basically an insulator. So, okay, so there's the solution. The solution only exists for r bigger than r plus, where r plus is the first 0 of f. The coordinate theta must be periodic. Whoops. Let's see. Whoops. Let's go back. Okay, here we go. Where f vanishes, theta has to be periodic so that it's smooth at that tip. So that theta becomes a usual standard angle. The period of theta is fixed in terms of the derivative of f at the tip in the usual way. This is familiar from the Euclidean black hole metrics. The Maxwell field you get by analytically continuing the magnetic charge on the black hole is, again, just constant. The x I guess I should say X-tau component is E. But this is now regular everywhere, right? You've cut off the geometry at f equal to, at r equal to r plus. There's no horizon. Tau is a good coordinate everywhere. So this is the answer. It's that metric I wrote down. This Maxwell field now is an exact solution. And that's all you have. You have an electric field. There is no induced current. So as expected, the solution describes an insulator. But the interesting point is that the solution only exists up to a maximum value of the electric field. You can solve for the electric field in terms of the length of the circle of theta, which after all is just the length of a circle in the dual 2 plus 1 CFT, and this parameter r plus. And you get a formula like this, which shows that E squared grows like r plus cubed and then falls like r plus to the fourth. So there's always a, so there's a maximum value to the electric field. This point here, where the electric field vanishes, is the standard ADS soliton solution. So as you increase E, you see that the tip moves in, and then it has this maximum value of E. So the maximum value of E, the critical value, it's equal to pi squared over L squared. I'll remind you that 1 over L is the scale for the mass gap in this theory. And you can ask what happens for E bigger than this critical value. And we expect that this solution simply collapses down and forms the black hole that we've been talking about. And evidence for that is the fact that if you look at the mass of the ADS soliton, the solution right here, is negative. It's actually lower than the mass of pure ADS. But as you add the electric field, the mass increases. And right at the tip here, the mass vanishes. In other words, it has exactly the same mass as the lowest mass black hole. So it suggests that as you increase the electric field just a little bit higher, the soliton will collapse down and form a black hole. That's, of course, exactly what you expect, because once the black hole forms, the current is non-zero, and the system starts heating up. And the interpretation from the dual field theory side, or from the insulator side, is that you have an insulator, but if you apply a strong enough electric field, you can create charged particles and induce a current. So now let me ask what happens if you go beyond 4 dimensions. So far, the solutions have been very simple, analytic, exact, and all in 4 bulk dimensions or dual to a 2 plus 1 dimensional system. Unfortunately, the simplicity does not extend to other dimensions. So if you go to higher dimensions or lower dimensions, you still have, of course, the planar Schwarzschild solution written in these ingoing Eddington coordinates. It takes a form very similar to what we had before, where f now goes like r squared minus a constant r plus to the d minus 1 over r to the d minus 3. And the temperature of the black hole is, again, proportional to r plus in a formula given there. You can, again, solve the linearized Maxwell equation. This fxv equals E gives you the right boundary condition at infinity, but unfortunately, by itself, it doesn't solve the Maxwell equation. You need to add an explicit XR term. But in fact, it's a good thing you need to add an explicit XR term, because as we've seen, this induces, this has a component in terms of the usual Schwarzschild coordinates, which is an XR component going like E over F, or goes like 1 over R squared. And in higher dimensions, that's not the right fall off to induce a current. The current comes from a higher power of R. So in fact, you have to subtract off the E over F term, that's the minus 1, and you find that you get a R plus over R to the d minus 4. This solves the Maxwell equation, and it's also the right fall off to induce a current. The current is, in fact, just this coefficient, E times R plus to the d minus 4. And so the conductivity, which is J over E, is R plus to the d minus 4. That can be rewritten in terms of the temperature, and you find that the DC conductivity in any dimension goes like this power of the temperature. That's, again, something that you expect because the conductivity is dimensionful in more than 2 + 1 dimensions, and the only scale in the problem is the temperature, so you'd expect it to go like a power of t. Now you can ask about the nonlinear corrections to this. Here we don't have exact solutions, so we have to do everything perturbatively. And so we calculated the back reaction up to third order, and you find that the current now does become time dependent, even for constant E. But the whole time dependence can be reabsorbed in terms of an effective time-dependent temperature of our black hole. Our black hole is growing. It's time-dependent, so there's not a real equilibrium temperature. But you can take the formula for the temperature of a static black hole, which is 1 over 4 pi times the radial derivative of f, and simply use that now as a function of v. So this would give you the right temperature in an adiabatic situation where the black hole was evolving slowly. And you can also argue, even for an abrupt change in v, that this is the right formula from the form of our metric, where the metric is an explicit function of v. So a certain change at v on the boundary propagates in along the null surface and affects the black hole at the same retarded or advanced time, the same time along an ingoing null vector. So this is a plausible definition for a temperature for our time-dependent black hole. And in fact, you find that, I mean, the formulas are now getting complicated, but the DC conductivity has a time dependence which is entirely absorbed in terms of this effective temperature, and then you get corrections that go like E squared and things like that. And the solution no longer is isotropic because the XX and YY components have different higher order corrections. Okay. So that's basically all there is for this simple model of the conductor and the insulator. And as predicted, I now have lots of time left to tell you about something else, which is work I've been doing with David Tong and my postdoc George Santos for the past year and a half on what happens when you compute conductivity as a function of frequency holographically in a system which doesn't have time, space translation invariance, where we've added a lattice. Well, let me first just remind you of the simplest model of a conductor, the Drude model. And this, well, it goes as follows. If you suppose electrons in a metal satisfy an equation like this, mass times acceleration is the force due to the electric field, minus mv over tau. This is a damping term, a dissipation term, and tau is like a relaxation time. If you assume that there's n electrons per unit volume, the current is just n times the charge times the velocity. Applying an oscillating electric field, you can easily solve this for the velocity, compute the current, find that it's proportional to the electric field, read off the conductivity now as a function of frequency, and you get this formula. A constant k times tau over 1 minus I omega tau, and k is just proportional to the number density of electrons. Okay, this is the oldest model of a conductor, very standard thing in condensed matter physics. So now we're going to go to the gravity side, and we're going to again work with the simplest model we have, just an Einstein-Maxwell theory in 4 space-time dimensions. We're again going to work at finite temperature, which means that we have to have black holes. But now we want to have finite density. We're going to add charge to the black hole so that the asymptotic form of the time component of the vector potential goes like mu minus rho over r plus higher order terms, where mu is the chemical potential and rho is the charge density in the dual theory. Now we're going to add a lattice by making the chemical potential be a periodic function of one spatial direction. So we're going to assume that mu is equal to some average value, mu bar, times 1 plus a naught cosine k naught x. So we have some amplitude of the oscillation a naught and some wave number k naught. We numerically find solutions. So this is numerical and no longer analytic. And I should say all the numerical work, and it was extensive, was done by George Santos. the numerical work, so we find these solutions which are static and translationally invariant in one direction. We're imposing the lattice only in one direction, but we're going to compute conductivity only in the direction of the lattice. So the solutions are rippled charged black holes. You impose this periodic boundary condition at infinity, and you find that the horizon itself has some periodic oscillation. Here's a plot of the charge density as a function of x. The scale is 0 up to 4 up here. So these are not small perturbations. These are large effects on our background black hole. You perturb the black hole, compute the conductivity, and you discover that at low frequency, the conductivity follows exactly this Drude form. On the left is a plot of the real part of the conductivity as a function of frequency. On the right is the imaginary part. And you always find that it follows this simple model for some constant k and relaxation time tau. More interestingly and surprisingly, we discovered that at slightly higher frequencies, there is a power law in the absolute value of the conductivity. So it goes like a constant b over omega to the 2/3 plus a constant offset c. So that's illustrated here on a log-log plot, where we plot the absolute value of the conductivity minus the offset as a function of frequency for 4 different temperatures. And you notice that for some intermediate frequency, these are all straight lines. The power minus 2/3 is extremely robust. We've tried changing all the parameters in our model, and it's always 2/3. The fact that the lines are really on top of each other shows that this coefficient b is temperature independent. Then you go to the condensed matter literature, and you discover that there is data on one of the cuprates. This is commonly known as BISCO. These are these high temperature superconductors, but we are looking at temperatures above the superconducting transition temperature. So this material becomes superconducting at about 95 degrees Kelvin. This is data from 100 up to 260 degrees by van der Merel et al. And he plots the absolute value of the conductivity as a function of frequency on a log-log plot, finds exactly the same mid-infrared power law, and the power that he sees is minus 2/3. This is a result we've had for over a year now. It's striking. We don't understand why. We don't understand why the gravity is predicting minus 2/3 so robustly, and we certainly don't understand why our simple Einstein-Maxwell theory is giving results that agree with BISCO. Well, I'm going to show you data in a couple minutes that has various dopings. There's a class of materials here where you change the doping. And for a large range of dopings, you see this in BISCO. I'm not aware. I've heard actually, maybe, I don't know if Sabir, you want to comment on whether this is seen in other materials or?
It's similar, but I think it's not that easy to do the experiment on. But I have another point, which is the frequency range over which they see this is quite different from your frequency range, isn't that right?
Yes.
Here the frequency omega is much greater than t. You could put t equals 0 and you still see this in the data. Whereas your ranges are bounded by powers or temperature.
I mean, we can have frequencies bigger than temperatures, but it's parametrically related to the temperature.
If you put t equals 0, would you see this regime?
No, if t equals 0, then you get the delta function again, because we don't have impurities, right? So
certainly, there's a delta function, but let's ignore at finite frequency. There's still some optical conductivity.
Oh yeah.
Even at t equals 0.
Right. Sure.
And the experiment, as far as we know, even at t equals 0, you see the omega to the 2/3 at finite frequency.
I see.
It's not part of the Drude peak at all. Whereas your theory,
it's certainly part. It's
comes out from the Drude peak when the
coming
experiment
off of the Drude peak. That's correct. Yeah. Okay. Well, let me go on, because there's a sort of an interesting twist to the story. So as I said, we've noticed this. We've had this result for over a year. Last week, we got an email from Sean Hartnell. I don't know if he's arrived yet. anyway, he's not here. Good, so I can talk about him. Sean Hartnell wrote to us and said, you know, I'm really not convinced that you have this power law because there's freedom in this constant offset. And you can sort of, and it's only a finite range, right? We don't see an arbitrarily large power law. You can sort of mistake a function that, you know, looks like a power law because you give yourself the extra freedom of the constant offset. So what I want you to do is to plot this. Omega times the second derivative of sigma over the first derivative of sigma plus 1. You notice the constant drops out of this function. And furthermore, if a sigma was a power law, this function would give you the power. It just gives you, this should be constant and equal to the power. So he says, take your data and plot this. Well, this turns out to be an extremely difficult thing to compute numerically, because you can notice that, I mean, if there's any sort of numerical jiddle in your data, you can find that sigma will, the derivative of sigma can vanish because of a little wiggle, and so this has a huge effect on this function. But nevertheless, George worked very hard, and last week, he couldn't use our old data. That was much too rough. So he improved the data using every trick in the book and came up with this amazing plot. So here's a plot of this function as a function of frequency. And you notice that over essentially the whole range we see the power law, it's constant and equal to minus 2/3. There's no fit here. You don't gain anything by a constant offset. We're not fitting to anything. You just plot the function, and it's bang on right on minus 2/3, showing that we really do see something which is looking just like a power law with minus 2/3. These blips, we believe, are resonances that have an amplitude too small to see when we just do a log-log plot. They're very tiny little things, but they are something that we have seen before, because well, we had seen when you go to larger frequency and you're outside the power law regime, there are rather pronounced resonances, which we have understood as a result of quasi-normal modes of our charged black hole. Quasi-normal modes, I remind you, are simply modes that are purely ingoing at the horizon, normalizable at infinity, and they exist for only a discrete set of complex frequencies. And it's been, well, known for 10 years now that they correspond to poles in the retarded Green's function, and therefore they show up as resonances in the optical conductivity. And you can fit a formula like this to the resonance and read off what the quasi-normal mode frequency is. So these little blips, I mean, George has gone back and blown up the data and actually sees these little bits and seen that it actually fits very well with this formula. So we know what these are, and when you're away from a resonance, we clearly see the power law.
The lifetime of the quasi-normal mode is some power of temperature or something?
Yeah, so the fact that these are so narrow, right, means that the imaginary part's very small. And I mean, we just got this, last week. We haven't looked at temperature dependence. I mean, this is very hard to do now. We've done it for one temperature, one.
So these are below the main bump that you see in the conductivity?
Yes. This is actually part of, you don't see it, but it's actually right here. Little bits here, little bits there. I mean,
but isn't it strange that they have decay rate that is, in fact, smaller than larger than the higher ones? Usually it goes the other way around. Typically, because normal modes usually...
Yeah, I know what you mean. That usually they sort of increase with frequency. No, so they grow. I mean, typically there's this plot where sort of the imaginary part gets bigger as the real part gets bigger, right? So we're now down at very small real parts, and so they're very small imaginary parts. I think that's going the right way. Okay, anyway, I have just a few minutes left, so let me tell you about the superconducting regime. So we then added, we wanted to know what happens when you go into a superconducting regime. So we just took the standard Einstein-Maxwell theory and added a charged scalar field to it. It was shown back in 2008 by Gupser that this model has a feature that at very low temperatures, charged black holes become unstable. They want to develop scalar hair outside the horizon. The stable configuration has scalar hair. Chris Herzog, Sean Hartnell, and I then followed up and showed that this was, in fact, dual to a superconducting phase transition. You have a second-order phase transition. The DC conductivity becomes infinite. Everything that you would expect. This is the holographic superconductor. And so we impose our same oscillating boundary condition for mu, and numerically find the solutions, which at low temperatures now have non-zero scalar field, a Ripley horizon. These are hairy, rippled, charged black holes. We again compute the conductivity as a function of frequency by perturbing these black holes. And you find that at small frequency, the conductivity is well fit by adding a pole in the imaginary part to the standard Drude formula. There's a Kramers-Kronig relation which relates this pole to a delta function at omega equal to 0 in the real part. And that delta function is telling us that we have a superconductor. So you get the infinite conductivity of a superconductor even in the presence of a lattice, as well as a normal component. So it's like so we have, well, I'm running out of time. Basically, you can plot now the normal component density. It drops very rapidly. The superfluid density rises when you go below Tc. The normal component density has a fall off, which looks like, it goes like e to the minus delta over t. So this is very much like BCS theory, where you have some thermally excited quasi-particles at low frequency, frequencies below the gap. The interesting thing is that the gap we read off from here is larger than the sort of BCS gap. We find that this goes like 4 times the critical temperature rather than the more standard 1.7 or so. Let me go on because the interesting thing here is the power law. If we go to, again, an intermediate range of frequencies, the absolute value of the conductivity, again, scales exactly in the way we saw before. This is for 4 different temperatures. The blue curve is T equal to Tc. So that's the curve we had before without any condensate, without any charged scalar field turned on. These are lower temperatures with the scalar field. And you notice that they just agree after a certain frequency, all having the same power law and the same coefficient. So these are just totally independent of temperature. In our gravity model, you go to the data, and you see exactly the same thing. So this is now 8 different samples of BISCO, which differ in doping. So you start with some underdoped sample with critical temperature 67. You increase the doping. There's an optimally doped sample with temperature 96. And then you go to an overdoped regime, and the temperature drops again. The critical temperatures drop. Each of these plots is a log-log plot of the absolute value of the conductivity as a function of frequency for a range of temperatures. And all of these temperatures start very high at like 295 degrees Kelvin and go down well below the critical temperature, 29 degrees Kelvin. And they all show this mid-infrarange power law with a coefficient independent of temperature, just like we see on the gravity side. So once again, we don't know why it works, but it does seem to be agreeing very well in this respect with the actual material. Now we have very preliminary results on a fully 2-dimensional lattice, which show very similar results. The conductivity in each direction is very similar to the 1-dimensional results. And so let me just summarize. I've shown you that there's a simple holographic model of a conductor which includes the Joule heating. The pressure remains isotropic. There's a simple model of an insulator which supports a constant electric field only up to a critical value, beyond which it becomes a conductor. Adding a lattice, we find an intermediate frequency power law with this exponent minus 2/3, which comes out very robustly on the gravity side, and exactly the same exponent is seen in some of the Coop rates, both above and below the critical temperature. And I'll stop there. Thank you.
I'd like to make a comment on your first part. We have, in fact, found a similar solution from a dBi action of a light-like electric field, which gave rise to a stationary solution. I don't remember the details now of how it compares with your solution, but in that case, what we found is that this brought the symmetry from conformal, of course, which was original, to Schrödinger, and where the conductivities now were nonlinear. And in fact, they depended on the electric field. That was in 5 dimensions, but in dBi, no back reaction.
Okay.
And we also found that the conductivities looked qualitatively similar to the overdoped region at very low temperatures of cuprates. I cannot tell you exactly what's the relation of that solution to yours, but I can look it up later on.
Okay, good. I'd like to have the reference. Thank you.
Maybe one more question.
Yeah, so it's about the second part of your talk. So I would expect that when you increase the amplitude of your lattice, eventually you may see a transition to an insulator. Did you try to see that?
We have increased the amplitude a bit by a factor of 4, and we don't see that yet. But of course, numerically, it's hard. So I can't say what happens for very large amplitudes.
Why would you expect it?
I mean, you have usually a superfluid insulator transition when you increase the amplitude.
Only at certain commensurate
Yeah,
densities.
exactly.
And,
The question is that whether you can tune this.
yeah, but this theory doesn't know about quantization of charge. Okay, I'm going to come to that one.
Well, they have a pointer here. I can give you mine.
Oh, this is it.